Waves are one of those topics where the equations show up fast and the topic starts looking very mathy very quickly. Sine curves, lambda, frequency f, period t, equations everywhere. So before we write even a single formula, I want you to understand what's physically happening on the string, what each tiny piece of the string is actually doing, and how that motion gets passed along. Once that picture's clear, the sine and cosine math will feel very natural. Now, strictly speaking, what we are dealing with here are mechanical waves. By definition, a mechanical wave is a disturbance that requires a physical medium, like water, air, or a rope, to propagate. We generally classify these into two distinct types based on how the particles of that medium move relative to the energy flow: longitudinal and transverse. In a longitudinal wave, like sound, the medium oscillates parallel to the direction of the wave. However, in a transverse wave, the particles oscillate perpendicular to the direction the wave travels. For this lesson, we will be focusing exclusively on transverse waves. So, many students imagine that a wave is a thing that moves forward, carrying the string along with it. Well, that's not what happens. A wave is a traveling pattern where each bit of the medium only oscillates around a fixed point. Let's prove that idea using the simplest system, a taut string, and build that picture from scratch. Imagine a long string stretched tight under tension. Give one end a single quick up and down jerk. You'll create a one-time disturbance that travels down the string. That traveling bump is called a pulse. Now, the next obvious question is, why doesn't the bump just stay where you made it? Why does it move forward? Let's break down exactly what happens mechanically. But before we do that, you must note that here we consider only an ideal string with no damping, that is, no air resistance or internal energy loss, so the amplitude doesn't decay as the wave travels. We also assume that the string is so long that we need not think about a wave rebounding back as it reaches the end. Another important assumption is that the amplitude is small, so the tension is essentially constant while the wave travels. Okay, so to understand this, that is, why does the bump move forward, don't just think of the string as one continuous line. Instead, I want you to imagine it is a long line of beads or segments. Take a look at this animation which zooms in on an interaction between two neighboring beads on the string. Notice the blue arrow pointing up and to the left. That represents the tension force pulling the next section upward. That is, the previous section of the string yanks the next section up. This upward force is what causes the disturbance to move forward along the string. But crucially, Newton's third law kicks in here. Forces always come in pairs. As the first section pulls the second one up, the second section pulls the first one down. That is the red arrow you see. So the blue force ensures the wave propagates forward by raising the next bead, while the red force ensures the previous bead is pulled back down toward equilibrium. This handoff happens continuously, atom by atom, down the entire length of the string. That is why the shape moves forward at velocity v, but the material just bobs up and down. And what is important to note is that the speed of a wave depends on the properties of the medium, more specifically tension and the linear density of the string, and not by the properties of the wave itself, such as its frequency or amplitude. Consequently, the medium, the string itself, does not undergo any net forward displacement. Instead, its individual elements oscillate perpendicular to the direction of energy propagation. This cutting across the path of travel is precisely why we classify it as a transverse wave. So you must distinguish between the particle velocity, v sub particle, which represents the vertical oscillation of the medium, and the wave velocity, v, which is the speed at which the disturbance propagates. Confusing between the two is a common pitfall, but understanding the distinction is the key to solving wave mechanics problems with precision. Now let's transition from a single pulse to continuous motion. So, if you oscillate the end in continuous simple harmonic motion, you generate a continuous train of pulses traveling at velocity v. Because the source of the disturbance is sinusoidal, the shape of the wave traveling down the string is also sinusoidal, taking the form of a perfect sine or cosine curve. Importantly, this means that every single element of the string is being forced to execute that same simple harmonic motion as the wave passes through it. This connection is vital because it allows us to use the mathematical language of sine and cosine functions to describe the wave. And that is exactly what we will tackle in the next lesson. We will define the specific parameters that govern this motion, such as the time period, capital T, the wavelength, lambda, and the frequency, f.